So let me briefly review our discussion from last time. We set up the general structure of supersymmetry, a Hilbert space with Z2 grading on Hilbert space vectors and operators that are Z2 graded. Okay, and we then looked at an example. The example we looked at was an example of supersymmetric quantum mechanics, non-relativistic supersymmetric quantum mechanics, with the one complication that wave functions were not just square integrable functions of position, but that there were two components square integrable functions of position. And so our wave function psi was, of this form, psi1, psi2. And on this space, we defined these operators. Q1 was equal to half sigma 1 plus sigma 1p plus sigma 2 w of x, and Q2 was equal to half sigma 1 how it is, was it sigma 2p minus sigma 1 w. Let me check. I think this was right. Right, minus half sigma 1 w of x, where w of x was any function. Now something that became clearer when you asked me your question, right, is that we want to insist that w of x is a function. Okay, by which I mean if I give you x, you give me a unique answer for what w of x is. Because for instance, w of x is going to enter a Hamiltonian. It's going to tell us what the energy of the particle is when it's at position x. And there should not be three answers to that question. Okay, so we're not going to allow functions that do something like this, that bend back for w of x. What is your name again, please? Sorry. Ajay. So Ajay asked me, as I will briefly review, I had said that every time we have a cut, if this is one slope, the other cut is the opposite slope. And Ajay said, well, what about function? He came and asked me, what about functions like this? This is only possible if you allow multi-valued functions of w, which we're not going to allow. Okay, so w is a genuine function. It's not some multi-valued function of x. Okay, but other than that, there was no restriction over w's. Okay, and then we argued that the anti-commutation relations of these two supercharges was q1 anti-commutator q2 or qi anti-commutator qj was equal to delta ij times the Hamiltonian, where the Hamiltonian was half p squared plus wx squared plus sigma 3 h bar w prime of x. Okay, then we did a semi-classical treatment of the ground states of the system. First, classically, we noticed that the ground states are all those states in which wx is equal to 0. Classical ground state. We noticed that semi-classically, these classical ground states behaved as follows. Suppose we're at a point, let's say xi, such that w of x is equal to 0. So around xi, if we expand the w of x, we get w is equal to alpha I x generically, where alpha is some number because it vanishes, x minus xi, sorry. Alpha I x minus xi because it vanishes at x equals xi. And then we noted that the harmonic oscillator 0-point energy, if we did the first semi-classical expansion here, told us that the energy of our state was h bar mod alpha I by 2. That was from the bosonic harmonic oscillator. And then depending on whether our state was up or down, we will get either plus or minus. We would get either plus or minus with plus h bar alpha by 2 plus minus depending on whether the plus minus was whether we were in this state or in this state in spinor space. Okay? Let's call this guy up and this guy down. Okay? So we saw that we got two options for the energy of this classical ground state when we worked semi-classically, which was this minus this. And then we saw that if alpha was positive, and we chose the down state, okay, then we would get a zero energy state. Okay, alpha positive means cutting the x-axis like this. So if we chose the down state here, we would get a zero energy state. Okay, on the other hand, when alpha was negative, we need to choose the up state, right? So that if alpha is negative, then we choose the up state, and that cancels this. That was the ground state. Okay, so semi-classically we saw that there were as many ground states as zeros. The ground states didn't get doubled because of the two component. One of the two components was chosen out. Okay. Then we did the exact analysis of this problem. Okay, the exact analysis of this problem was to find the ground states was just to solve the equation q1 on psi was equal to 0. This is a first order differential equation, so it's sort of easy to do. The equation is that it tells us that P is equal to minus sigma 1 sigma 2 W. That is what the equation becomes. P is sigma 1 sigma 2 is I times sigma 3. So we get minus I times sigma 3. But P was minus I del by del x. So we get minus I del by del x. Minus I is cancelled. And so the equation we had to solve was del by del x on psi is equal to sigma 3 omega on psi. And that was an easy equation to solve. Psi was equal to exponential of integral sigma 3 w of x dx, let's say from 0 to x, acting on some psi naught. And then we argued that if this psi naught here, then we argued that if this w was of this structure, for instance, so that went positive up here and went negative up here, then choosing psi naught equals down, in that case psi naught equals down would give us one acceptable normalizable ground state, right? On the other hand, if we had a w of this form, then psi naught equals up gave us one normalizable ground state. Finally, if we had a w of the form that, at something like this, no choice of psi naught gave us an acceptable ground state. So the number of ground states in the actual problem was either 1 or 0, depending on the nature of that our w. Okay, this kind of w, or this kind of w had exactly one ground state. This kind of w or its inverse had no ground states. Okay, and notice that this kind of thing, which was coordinated with this, let's draw this. Okay, whereas this was coordinated with this. Notice that this had 2 downs and 1 up, 2 downs and 1 up, or 1 more down than up. There the ground state was actually a down. Whereas this, which had 1 more up than down, the ground state was actually an up. Then we discussed the Witten index. Okay, we talked about how there was this lovely quantity called trace minus 1 to the power f times e to the power minus beta h. Okay, this quantity received contributions only from ground states. The argument for that went as follows. You remember we had the supersymmetry algebra. Okay, so to make this, you might remember I got stuck in making this argument, so let me do it correctly this time. we have our supersymmetry algebra is Q1, Q2, Qi, Qj is equal to delta ij h. But for many purposes, it's sometimes useful not to work with the supercharges Q1 and Q2, but instead they're complex linear combinations. So let's define Q is equal to Q1 plus IQ2. Okay? And Q bar is equal to Q1 minus IQ2. Since Q1 and Q2 were Hermitian operators, Q and Q bar are Hermitian daggers of each other, as you see because of the eyes. Okay. Now, what is the commutation relations between these Q and Q bar? Of course, Q and Q bar contain all the information in Q1, Q2, just another basis. What is the commutation relation for Q and Q bar? It's easy to check that Q squared is 0, because Q squared is anticommutator of Q1 plus IQ2 with itself. This gave us plus h, but this gives us minus h. Q1 with Q2 anticommutator gives 0. Okay, so Q squared is 0, Q bar squared is equal to 0, same argument. The minus came because I square was minus 1, but minus I square is also minus 1, so same argument. Okay, but if you do Q with Q bar, then instead of cancelling, the Q1 squares and the Q2 squares add up. Okay, so if you do anticommutator of Q with Q bar, you get 2h, because Q1 with Q1 gave you h, and Q2 with Q2 gave you h, so they add up to give you 2h because the signs conspire to add up. Okay, so this is an equivalent set of commutation relations, which is for some purposes more convenient. Okay, since we've said this, let me also just write out the form of Q and Q bar in this particular model. So Q, let us define sigma plus is equal to sigma 1 plus I sigma 2. Now, remember that sigma 1 was equal to 0, 1, 1, 0. But sigma 2 is equal to 0 minus I 0. So I'll define this with a by 2. So sigma plus is sigma 1 plus I sigma 2. You see, if I do a plus I, this becomes 1. This becomes minus 1. When you add it up, these two cancel each other. These two add up. Because of the by 2, this sigma plus is just the matrix 0, 1, 0, 0. It's the guy that raises minus to plus and kills plus. I mean, minus, it raises down to up and kills up. Similarly, I'll define sigma minus is equal to sigma x minus I sigma y by 2, and you find that sigma minus is equal to same algebra, I mean similar algebra. Yes?
According to our convention, that should be h, right? Not 2h.
No, 2h.
Because qi, qj, anticommutators, delta ij, h, right?
Good. So let's work it out. So suppose we have q1 plus iq2. Okay? Anticommutator q1 minus iq2. Now these are 4 different anticommutators. Q1 with Q1, 2 of them are 0. Q1 with Q2 gives 0, and Q2 with Q1 gives 0. So this is equal to Q1 anticommutator Q1. Okay? Now I and minus I cancel each other. So plus Q2 anticommutator Q2. Each of these is h. So that's equal to 2h. Is this clear? Okay, I could have made it h if I'd put some square root 2's, but I just didn't feel like. All good? Yeah. Okay, excellent. So this is a bit of an aside, by the way. I'm going to use these q's and q bars in the argument, and it's a useful thing to Keep in mind, Q's and Q bars are often more useful to work with than Q1 and Q2. Just like, light cone coordinates are often more useful to work with than X and Y. It's that same thing. So just for completeness, I'll tell you what, in this model, we'll work out what Q and Q bar are explicitly. Okay? So now let's see. Let's look at Q. Q is Q1 plus IQ2. But sigma 1 plus I sigma 2 is sigma plus. So the term with P is Q is equal to sigma plus, the by 2 goes away, times P. Now let's look at the W term. The W term is sigma 2 minus I sigma 1 by 2. Is it clear? Because I'm taking Q1 plus IQ2. So sigma 2 by 2, okay? And then there's the minus sign, but there's the I sigma 1 by 2. But this is the same thing as minus I into sigma 1 plus I sigma 2 by 2. So it's equal to minus I into sigma plus. Okay? And therefore we find that this is sigma plus minus I W of X. Okay? And similarly, by doing very similar algebra, you will convince yourself that Q bar is sigma minus in a P plus I W of X. So you see, even at the level of the explicit operators, Q and Q bar are somehow nicer. The both terms are proportional to the same sigma matrix, rather than having different sigma matrices. This was just an aside. It's not very important. Okay. So if you remember, in discussing the Witten index, what we discussed is the following. We talked about how supersymmetry operators, since all supersymmetry operators commuted with the Hamiltonian, we can implement the supersymmetry algebra energy state by energy state, meaning fix a particular value for the energies of your states. That set of states, the set of states with those energy values, give you a representation of the supersymmetry algebra, but a representation of the supersymmetry algebra where the Hamiltonian is replaced by a number, namely the energy. Is this clear? The fact that supersymmetry commutes with the Hamiltonian tells you that when you act on one state, a state with a given energy, with the supersymmetry operator, you don't change its energy. So that algebra has to be implemented consistently, just directly on states of that given energy. Then we discussed that there were two inequivalent kinds of energies. There was 0 and positive. You remember we explained that the Hamiltonian could not have negative eigenvalues because it was a perfect square. Okay? H is Q1 square, Q1 is a Hermitian operator, therefore all its eigenvalues are positive definite. Okay? So the only possibilities were either 0 or positive. Then we explained that the positive eigenvalues, suppose I have a positive eigenvalue, first, suppose we have 0 eigenvalue. All the supersymmetry operators are implemented by the number 0 on that representation. And such representations were one-dimensional. The irreducible representations were one-dimensional. Okay? So supersymmetry representations were one-dimensional when energy was 0. And I wanted to convince you that the supersymmetry representation, the irreducible representations, were two-dimensional when energy was not 0, and I got confused in trying to make the argument. You can make it in many ways, but it's much easier to make it using this Q and Q bar. Okay, so let's work with Q and Q bar. And let's normalize them. Let's define Q is equal to Q divided by 2 epsilon, where epsilon is the energy of the state we are considering. Okay? And Q bar is equal to Q bar divided by square root of 2 epsilon. Now we get the algebra Q anticommutator Q bar is equal to 1. This is Q square equals 0, Q bar square equals 0. Now let's suppose we've got some state. Let's call the state chi. Okay? Either this state is annihilated by Q or it's not. If it's annihilated by state Q, good. If it's not, I will define a new state which is Q on this chi. Now this new state is annihilated by Q because Q squared is 0. Okay? So you give me any state and I can from it make a state in the same multiplet that is annihilated by Q, either the state itself or by acting on it by Q. Okay? So you give me a state and I will give you a state in the same multiplet which is annihilated by Q. Okay? So let me assume that this state chi is one of these states annihilated by Q. If you gave me a state that was not, I make one out of it. Now, I want to find the whole multiplet. So there is chi itself. Now I could try acting on this by Q, but that doesn't do any good because that chi is annihilated by Q. I can act on it by Q bar. That's fine. Okay, so let's define Q bar chi is equal to psi. That's the second state. Okay, we will soon see that it's impossible for, at least naively it's a second state. We will soon see it's impossible for then this state to be 0. You might have wondered, what if this is 0? Okay, okay, let's immediately see that. Suppose Q bar on chi was 0. Then Q bar plus Q bar Q on chi would be 0. Because we know Q is annihilated by, chi is annihilated by Q. And you've told me that chi is annihilated by Q bar. So both these terms annihilate chi. So we will get 0. Okay? But we know that on this representation Q bar plus Q bar Q is implemented by 1. So that's a contradiction. So it's impossible that chi is annihilated by Q bar. Is this clear? Okay? So there must be at least 2 states in every irreducible representation. We found 2 of them. We found chi and psi. Now, let's take the state.
Q annihilates it, then Q bar cannot
annihilate it. Unless energy was 0. When energy was 0, that's what happens. Both annihilate. Right? And the argument is clear? Okay, fine. So now let's look at psi. We can try to generate more states by acting either Q or Q bar on psi. We've got everything we could by acting with Q on chi, Q and Q bar on chi. Okay, now let's act with, so suppose I try to act with Q bar on psi. That is 0 because psi is equal to Q bar on chi and Q bar squared is 0. No good. Okay, what about Q on psi? So what about Q on psi? This is a potentially new state. But psi was equal to, but this is the same thing as Q bar on chi. Right? Because psi was by definition Q bar on psi, on chi. But this is the same as Q bar plus Q bar Q on chi. Because chi is annihilated by Q. But this is equal to chi. Because on our representation, Q bar plus Q bar Q is 1. It's the algebra. So what you get by lowering psi is not a new state. You go back to your old state. And so we're finished. We've seen that every irreducible representation is 2-dimensional. Is this clear? You can make the same argument using Q1 and Q2, but it's much more cumbersome. It's much easier this way. Okay? So all representations of supersymmetry at fixed energy are very simple. The irreducible representations are either 1-dimensional when the energy is 0 or 2-dimensional when the energy is non-zero. Notice that the 2-dimensional guys, okay, are related to each other by the action of some Q. Okay? Now that we've proved that this is the only possible representation, we can just write it down, right? So, Q is the operator, let's say, 0, 0 is sigma minus. and q bar is equal to sigma plus. This implements exactly what we had, right? Opposite, it depends on what you're calling down and what you're calling up. Okay, I was thinking of my chi as being down. It's annihilated by q, therefore q is sigma minus. But if you want to think of chi as up, you switch it. Doesn't matter. Right? Yes? Why psi cannot be 0? Psi cannot be 0. Good. You see, q bar on chi is equal to psi. Okay? Now, suppose psi was 0. Okay? Then, let's we know that chi is annihilated, q chi is equal to 0. We know this. Suppose q bar on chi, which was psi, was also equal to 0. Suppose. Then it follows from this, these two together imply that q bar plus q bar q on chi is equal to 0. Why? Because so the first term is 0 because q annihilates psi, and the second term is 0 because q bar annihilates psi. But this is impossible because we know we're trying to find a representation of an algebra in which q bar plus q bar q is 1. So we're not representing an algebra. Okay, so it can't be that. This is the famous statement. I mean, I'm repeating things you know very well. Somebody, when I was last started saying it's Clifford algebra, it's correct. It's a famous statement that the Clifford algebra cannot be implemented in a one-dimensional space. Had psi been 0, it would have been a one-dimensional implementation of the Clifford algebra. Impossible, right? We know this from very early on. Right? I'm just reiterating the reasons you've learned in your undergraduate studies. Okay, so the supersymmetry algebra is very simple. This is one-dimensional and two-dimensional representation. Notice, then we define this operator f such that minus 1 to the power f, really we define the operator minus 1 to the power f, such that minus 1 to the power f anti-commuted with every q. Let there be such an operator. Now you might wonder, is there such an operator? Well, the answer is yes, because we know that a Hilbert space is graded into bosons and fermions. So if we just let this f act as 1 on the bosons and on minus 1 on the fermions, it will automatically anti-commute with every q, because a q is an operator that takes bosons to fermions and vice versa. So if you put that together in your head, you will easily see that this construction, if I just choose f to act as 1 on bosons and minus 1 on fermions, I'm sorry, I said it wrong. F to act as 0 on bosons and 1 on fermions. I said 1 and minus 1, that was wrong. F to act as 0 on bosons and 1 on fermions, or minus 1, doesn't matter. On fermions, that construction will give you a minus 1 to the power f that anti-commutes with every supersymmetry. Okay? I'm just saying the following, that our Hilbert space is graded. So we can always choose a basis such that every operator has this Brock diagonal structure, such that this part is bosons and this part is fermions. Okay? So if you choose an operator that is of the form 1 and minus 1 here, identity and minus identity, then any operator that is off diagonal, and a supersymmetry operator is completely off diagonal, will automatically anti-commute with these, as you can easily check. Right? Same algebra as sigma 1 and sigma 2 commute with sigma 3, anti-commute with sigma 3. Same statement. Okay? So such an operator always exists. In our little model, we found that operator. Okay, we found our minus 1 to the power f was sigma 3. We found that operator explicitly. Okay? And then we argued that because of this because of the fact that non-zero energy states always appeared in a doublet with -1 to the one piece with -1 to the power f being 1 and the other piece with -1 to the power f being -1. The non-zero energy states did not contribute to the trace of -1 to the power f times e to the power minus beta h. This is clear, right? Only the zero energy states contributed to this. This tells us that while, zero energy states, their details can change. If our Hamiltonian, our system is being changed in some continuous way, so that states either ascend from zero energy into some non-zero energy or descend from non-zero energy into zero energy. They always ascend and descend in ways that don't change -1 to the power f. Only zero energy states contribute to this quantity. The structure of zero energy states is not rigid. It could be that you've got some zero energy states and then two of them leave when you change a parameter. Structure of zero energy states is not rigid, but what is rigid is the quantity -1 to the power f computed on the space of these zero energy states. Because they can ascend and descend only into non-zero energy states. You're assuming the spectrum is continuous. You're assuming that your change of parameters is such that doesn't do something violent to the spectrum of your theory. It's like a discontinuity. Okay? Because of that, you see, because of the continuity, the only way, let's say, that two states can leave the zero energy manifold is by going to slightly non-zero energy. But all states at slightly non-zero energy compared into pairs that contribute 0 to trace -1 to the f, because one is a fermion, one is a boson. Is this clear? Therefore, trace -1 to the power f is a very robust quantity. It cannot change under a deformation under which the spectrum remains continuous, varies continuously. Okay. This we've encountered in this very special model, but it's a true statement following from the supersymmetry algebra. So every time you have an algebra like this, and we will see as we go on in this course, we see, even more complicated supersymmetry algebras, we will often have this subalgebra. Q squared is equal to Q squared is equal to 0, Q bar squared is equal to 0, Q bar is equal to energy, twice energy. We will often have that structure. Okay? Whenever that's true, the same argument tells you that the Witten index is a very robust quantity, cannot easily change. Okay? Great. Now, and then the last thing we talked about was that we noticed that while the exact computation and our semi-classical treatment got this number of ground states wrong, it got the Witten index right. We've already noticed this here. Right here, this would have Witten index -1, and the actual ground state has Witten index -1. Here, this would have Witten index +1. The actual ground state has Witten index +1. Okay, I think that's really as far as we went in the last class. I'm sorry that this review took so long. Just it's been so long since we had our last class that I want to remind everyone about it. We'll have our classes regularly from now on. Okay, I'm sorry about all this. Okay, so any questions or comments before we proceed?
Excuse me, sir. How to see from the algebra of small q and q bar that the zero energy states are one dimensional? Because when we apply square root e factor denominator,
right. What? Wow. Okay. So let's look at q bar plus q bar q is equal to 0. Okay. Now let's look at this state. Actually, this is a bit easier. It's the same thing, but it's a bit easier to see directly from q1.
it's 1, right?
Sorry, is equal to 1. Thank you. Is equal to 1. Thank you. No, is equal to 0 because it's Hamiltonian.
But we divided by square.
Ah, so you don't want to divide by 0. Good. Good. So we are allowed to do that division by 0, by the energy, square root of energy, as long as the energy is itself not 0. If the energy is 0, you just don't divide. So then you get the algebra with capital Q. Capital Q bar plus Q bar Q is actually equal to 0. Okay? And now we want to show that this is actually implemented by Q and Q bar being 0. Okay? But how do you show that? You just take this and sandwich with psi. Okay? These are positive definite quantities. So they must be 0 individually. Right? Because Q and Q bar are Hermitian conjugates of each other. It's a bit easier to see with Q1, but okay, anyway. Okay? This one will tell you, this one being 0, tells you Q bar annihilates psi, and this being 0 tells you Q annihilates. So the state is annihilated by both Q and Q bar. Just trivial representation. Any state space this is annihilated by both Q and Q bar. You don't go anywhere in the representation. Is this clear? Okay. It's even easier to see with Q1. Q1 squared is equal to 0. Therefore, Q1 must annihilate the state. Q2 squared is equal to 0. Therefore, Q2 must annihilate the state. Same by using expectation values. Clear? Any other questions, comments? Okay, great. So all this is very nice, and I like this as a starting point to our analysis because it makes it clear what supersymmetry is. It's just some operator in the Hilbert space that happens to have some commutation relations with other operators. There's no need to talk about anticommuting numbers. There's no need to talk about even fermions in any real way. It is very down to earth. You see it in front of your eyes. This is what it is. Okay? However, as we go on, it will become increasingly cumbersome to deal with supersymmetry in Hamiltonian language. By far the best way to think of it when we work with field theories, for instance, will be in Lagrangian language. Okay? So, our next goal is to try to take what we've learned and turn it into some Lagrangian lesson. We want to understand everything we've understood now, but from the point of view of a Lagrangian, not from the point of view of Hamiltonian. Okay, so the question we're going to ask is the following. Suppose I've got this Hamiltonian here. I've got this Hamiltonian acting on some two component wave function, and I want to write down a Lagrangian for it. What is the correct Lagrangian? Well, you might say, well, okay, we just do the Legendre transform, right? We Legendre transform, and Legendre transform, p squared will become x dot squared by 2. The energy part will pick up a minus sign, and that's the Lagrangian. But wait a minute, a Lagrangian has to be a number. And if we do these procedures, what we'll get is some matrix, some 2 cross 2 matrix. So that's not right. Right? By Lagrangian, what we mean is a number. And the Hamiltonian itself was some 2 cross 2 matrix. So if we do the Legendre transform just with respect to x, we've moved from a function of momentum and position to a function of x dot and position. That's great. But we've still left with the fact that we're working with a 2 cross 2 matrix. You can take the trace, but that's not what the Hamiltonian was. Hamiltonian was the trace of this operator. It was this operator as a matrix. Right? So that won't work. Okay? So if we want to move to a Lagrangian for this system, because matrix kind of indices are sort of intrinsically quantum mechanical. They're already in the space of an operator acting on some Hilbert space. We're having trouble, right? Lagrangian is a nice classical notion, but we're dealing with a quantum object. Something similar happens in coherent space quantization. All of Gautam's students must know this. It's co-adjoint orbits. It's fun stuff. But anyway, right now we'll put that aside. Okay, so great. So what do we do? Well, this is of course a problem that people thought about a long time, and they came up with an interesting trick. And the interesting trick is that we can make the Lagrangian look sort of like a number. Sort of like a number if we enlarge our imagination. We allow ourselves to work on the space not just of ordinary numbers, but of anticommuting numbers. And this is what I'm going to describe to you now. Okay? All of you have seen this in some language, but we'll see it again and systematically. Okay? So what is an anticommuting number? P square and x were the operators. But now suppose
It has already a infinite dimension.
it has already infinite dimension. But you know, the classical version of the Hamiltonian had p squared and x equals numbers. Okay, so let's move to that classical version of the Hamiltonian.
In classical thing, sigma 3 is not there, right?
Okay, if you say it's not there, then correct, it's not there.
Yeah.
It would be not there. Okay, but then you're throwing away what you actually want to compute. I want to get a path integral representation of this problem, not of some truncation of this problem. Right? So you're right that the matrix part was sort of quantum, and you saw that with the H bar. But I want to capture that part through when I say Lagrangian, really what I mean is a path integral. I want a path integral representation of e to the power minus IH. Question is, how do I get it? Okay, what do I put in the integrand for the path integral? You may think of some path order, something or the other. Maybe you can try to be imaginative. But there is a standard answer to this question, which I will tell you. Okay. Fine. Now, I'm going to introduce these objects that people call anticommuting numbers, which, you know, these are the kind of things that mathematicians introduce. They're just formal objects that obey a bunch of rules. Okay? So, let's say we've got theta 1, or maybe what I will need for now is theta and theta bar as two anticommuting numbers. Okay? These anticommuting numbers obey the following properties. Theta squared is equal to 0. Theta bar squared is equal to 0. Though in our context it will be true, it's not necessary that theta and theta bar, and there's any sense in which they're complex conjugates of each other. Just independent anticommuting numbers. Okay? And theta theta bar is equal to theta bar theta. Okay? If I have minus. If I have more anticommuting numbers, theta 1, theta 2, theta 3, theta 4, they're always defined the same way. Each number squares to 0 because it anticommutes, its anticommutator with itself picks up a minus sign, which tells you that it squares to 0. And each number anticommutes with every other anticommuting number. This is the first rule of anticommuting numbers. Okay? Some formal object, you can find representations of these as matrices. But we don't need that. Just the formal properties is what we will need. Okay. Now, we will often think of functions of anticommuting. So let me, at this point, let me not restrict to just two. So I've got theta I. Theta I is, sorry, this looks like a Q, right? Theta I squared is equal to 0, and theta I anticommutator theta j is equal to 0, which is the same thing as theta I theta j is equal to minus theta j theta I. Okay, we've got a bunch of numbers that obey this property. As I said, you could find a matrix representation of this algebra, but we're not. So, okay, maybe that'll convince you that that exists in terms of something more familiar. But we don't care about that. It's just something. Now, yeah, theta bar is just another anticommuting number. It's one of these anticommuting numbers. Okay? Fine. Now, we're interested in making functions of these anticommuting numbers. The only functions we will allow are polynomials. Now, you see, really I should have said the only functions we will allow are those that have power series expansions. But because we've got a finite number of anticommuting numbers, at least to start with, and each number squares to 0. There's only a finite number of expressions you can make, and therefore you'll only get polynomials. Okay, so all our functions of anticommuting numbers will be just power series expansions. And if there's a finite number of anticommuting numbers, there will only be polynomials. Okay, so suppose we have, for instance, two anticommuting numbers, theta and theta bar. Then any function of these is of the form a plus b theta plus c theta bar plus d theta theta bar. So functions of anticommuting numbers are pretty simple objects, specified by finite data. Okay, note that this function is the same as a plus b theta plus c theta bar minus d theta bar theta, where a, b, c and d are ordinary numbers. Okay. Could be functions of ordinary variables, not anticommuting. Okay. Now, what we need to do, because we want to get a path integral, is to learn how to integrate and differentiate functions of anticommuting numbers with respect to anticommuting numbers. It could be, but then we would expand those coefficients as well. Okay, so we will keep expanding until every anticommuting number is explicit. Then it will always be of this form. Just might go longer, because then if these were functions of theta and theta bar, then you can always expand them and rearrange so that it's in this form.
No, I'm not saying that they are functions of theta and theta bar, but I'm saying b can't be a constant anticommuting number.
But
if it's an argument for theta is the argument, but as a constant there can like theta plus some epsilon which is
right. You may want to think of this as being some anticommuting number. And in some situations we will want to do that. Yes. Yes, you're right. You're right. Some situations we will want to think of these as being other anticommuting numbers. Absolutely right. What I should have said is that a, b, c and d have nothing to do with theta and theta bar. That's what I should have said. You're right. Okay. Okay. Now, the next thing we want to do is to learn how to integrate and differentiate with respect to this theta and theta bar. Okay? And we just define a bunch of rules. The rules we define are that d by d theta of theta is equal to 1 and d by d theta of 1 is equal to 0. Pretty reasonable, right? Constant has 0 derivative, theta has derivative 1. Now you might ask, well, what is d by d theta of theta squared? But that makes no sense because theta squared is 0. So it's all we have to specify. Now, of course, we may want to differentiate some expression that involves not just theta but also some theta bar, or other thetas in general. And then we make the rule that d by d theta of theta, let's say theta bar, is equal to theta bar. So you act from the left. However, d by d theta of theta bar theta is the same thing as minus d by d theta of theta theta bar, because theta bar theta was minus of theta theta bar. And so this is equal to minus theta bar. Okay? So the derivative eats up the theta if it's right on the left, completely on the left. If it's not completely on the left, you rearrange things to make it completely on the left. Effectively, what we've learned from these manipulations is that the derivative with respect to theta anticommutes with all other anticommuting numbers. Right? Because we just use that rule. We anticommute this derivative through the theta bar, then we get a minus sign, and then we act on the theta. Effectively, that's the rule. Because you have to move the theta through the theta bar to act on the left. Is this clear? So this is a reasonable definition. These are all reasonable definitions. Go on.
which we are considering here.
Ma'am?
We are intrinsically assuming that it has finite radius of convergence. What about functions like 1 upon
Yeah, we're never going to, oh, 1 upon x, we can define that. Oh, no, not 1 upon x, no. We're only going to look at functions that have a Taylor series expansion. It's an assumption. You see, all functions that we define are polynomials of this. The only functions are polynomials of this theta. Now, if you want to define a function that has, that would itself not have had a Taylor series expansion, would itself have had an infinite Taylor series expansion, you Taylor series expand it, and some terms it will stop contributing after a symbol. We'll see examples. Now, what about functions that have no Taylor series expansion? That we're not going to look at. Could be.
I was thinking about like in electromagnetism we have 1 upon r potential.
Right.
So we can have similar analog 1 upon theta potential.
Yes, it's an interesting question. You know, you may be able to define it in the following way. You may be able to define it by, we're not going to encounter such things, at least for now. But depending on your use, you may want to find an integral representation for that function, which itself has, where the integrand has a Taylor series expansion. Okay? So for instance, 1 over x is e to the power minus a xy integrated over y. Whereas e to the power xy has a nice power. So you may be able to get away with doing that. I would have to think about it. But that would depend on what you want to use it for. Okay? We're not going to meet such functions, at least at the beginning. If we do, we'll have to think about what it means. Okay, good question. Other questions?
You are assuming the product breaking rule. I mean, you are saying that delta theta of theta bar equals to theta bar. But if you apply, suppose assuming the product rule, you can separate that. I mean, del theta
Yeah.
theta bar plus something like that.
Yeah. So we assuming the product rule and using the fact that del by del theta of another variable is 0. It's 0 because it's an independent variable.
Okay. And if we apply this rule to the second thing, I mean the del theta of theta bar theta, then what will happen? The first term is 0 and the second will be theta bar. So why it is minus theta?
Because you have to anti-commute the derivative through. So what is the right product rule? The right product rule is that del theta of alpha beta is equal to del alpha by del theta beta minus alpha del beta by del theta. And it keeps going. Every time you take a derivative through something which is anti-commuting, it picks up a minus sign. Okay? Now you could figure that out by the following. Since alpha and beta were anti-commuting with each other, this alpha beta was the same as beta alpha. So like we did here. Okay? It's not something you have to postulate. It will turn out to be true. Okay, good. Okay, basically it's just that del by del theta on theta is 1 when it's on the left. If there's no theta, you get 0. And if theta is not on the left, you bring it to the left. And you get what you get. And that will tell you this rule. Okay, good question. Other questions? Okay, excellent. So, that's not a good bird. Maybe we can start clearing. Now, this is where things start becoming a bit weird, if you've never seen this before. We also want to define the integral with respect to theta. And we do this really weird thing. We define that integral d theta is equal to d by d theta. If you've not seen this before, this seems like it makes no sense, right? This is just a definition. That integral symbol with respect to theta, same as the derivative symbol. Sometimes we will need to integrate with respect to, we'll write d theta bar. Then what we mean is that this is d by d theta bar in the same order as our d thetas. Okay. These are bunches of rules that I've thrown at you. Okay. So far, it might seem totally unmotivated. It's like you're doing some crazy mathematics. What has this to do with physics? Okay. I'm now going to show you that this crazy mathematics is useful. It's useful for to solve the problem that we posed for ourselves. What is the path integral representation of the Hamiltonian we were interested of the Hamiltonian system we were interested in? Okay. The reference for the rest of this lecture is this beautiful appendix A in volume 1 of Polchinski's book on string theory, where he talks about fermionic path integral. It's beautiful. Only when I read that I felt I finally understood what these fermionic path integrals were. Otherwise, I thought, what is it? What's going on here? Okay. Okay. So I'm going to ask, suppose you have a two-state system. Our Hamiltonian was a two-state system times functions of variables, right? I mean, our Hilbert space was a two-state system times functions of variables. Functions of variables we know how to deal with. We know how to go from Hamiltonian to Lagrangian. It was these operators, these 2 cross 2 operators that had left us stumped. So the question we're going to ask first is a basic question. Forget the functions of the variables. Suppose you just had a two-state system. You have only a two-state system, and you've got some Hamiltonian on this two-state system. You want to try to write a path integral representation for e to the power minus I ht. How do you do it? Well, that's the question. Is the question clear? Okay. So our two-state system is the following. Our two-state system has a spin up and a spin down. Now we define, let me just make sure I'm not interchanging with Polchinski so that you don't run into trouble when comparing with him. We define the operator psi hat as the lowering operator. Psi hat, okay, so we define two operators which are basically sigma minus and sigma plus. So psi hat, which is secretly sigma minus, but it's an abstract operator, okay, such that psi hat on down is equal to 0 and psi hat on up is equal to down. The operator number 1, clearly you see it's sigma minus. Okay, then we define another operator, chi hat, which is secretly sigma plus, okay, such that chi hat on up is equal to 0 and chi hat on down is equal to up. Okay, this is secretly. Okay? Now we do the following fun things. We define a fermionic coherent state as the state psi we define to be down plus psi times up, where psi is one of these funny anticommuting numbers. Okay, what I was calling theta and theta bar before, some anticommuting number. Okay, so this is some state in the Hilbert space, but with some enlargement of what you mean by Hilbert space. You're allowing for these anticommuting numbers as coefficients in these states.
How do you define probability?
What?
How do you define probability in terms of
Probability? No, we'll never talk. This will be a formal object. This will not be a true state in the Hilbert space. Just appear in intermediate states and calculations. Okay. Yeah, should not give it reality. Just a mathematical trick to generate that Hamiltonian we're interested in. Okay. Now, so this is our state psi. Then we define the state psi, the bra psi defined so that bra psi prime is equal to psi minus psi prime. I'm going to solve for what this bra psi is. I'm going to solve for it to ensure that this is true. Okay? Actually, much of the analysis can be done without specifying what bra size. I'm going to specify it for you because it makes it more concrete. But much of the analysis can be done abstractly, and that's useful because some of you know, at least those who were in my string theory course know, that sometimes for two-state systems, it's useful to consider a non-positive definite inner product. We do that when we study the BC system. And okay, for this discussion though, let us assume that the inner product on a Hilbert space is the usual one. That is up is equal to 1, up, down is equal to 0, down, up is equal to 0, and down is equal to 1. Up and down are just orthogonal states. Let's assume we're working with this inner product. Sometimes physics forces you not to work with this inner product, but the cross inner product. Up down is equal to down up is equal to 1, up is equal to down is equal to 0. And then everything I say goes through for that. We needed that for string theory, right? It's just that the specific construction of the bra will be different. But just to make it concrete for you now, I'm going to give you more than the abstract argument. Okay, so we can find what this bra is. Okay, so this bra psi is equal to down psi plus up with this inner product. Assuming this inner product, this is this I claim is true. Now let's check. To check this, we need to check that psi down plus up inner product with down plus psi prime up is equal to psi minus psi prime. Is it true? Well, let's see. Down hits down and that gives psi. So it's not true, and therefore we need to change this to minus. Up hits up and gives us psi prime. But because of this minus, we get the minus then. All good? Okay. So this is the definition of psi, and if we of the bra psi. Note that it's not, it's not just turning these kets into bras. That's not what our definition is. This is what I mean by bra psi. It's this object. Yeah, you may think it's bad notation, fine. It's useful notation. Okay? And okay. Now, before we move on, you might wonder why did we
How many things you are assuming that this bra psi definition and this normal inner product?
this I'm assuming really this. I define bra psi. This equation defines bra psi. Now, if you implement a particular inner product, then this is the solution. If you had another inner product, you would find another solution. But we will not use the specific form of bra psi. Oh, you can get away by not using the specific form of bra psi, only using this property. So then, what the specific implementation of bra psi, though it will be the one we want in this context, is not important. Maybe I shouldn't have brought this up. Just to remind the people who've done string theory that the other inner product can also be dealt with in this. Now we can forget about that if you want. Okay. Okay. Now, one question. You might ask, what about this psi minus psi prime? That's a sort of weird kind of object, right? Why did you want psi minus psi prime? The reason we wanted psi minus psi prime is the following. Psi minus psi prime is the non-commuting version of a delta function. Why is that? You see, what property does delta function obey? It obeys the property that delta of x minus x prime, f of x prime, integral dx prime is equal to f of x. That's sort of the defining property of a delta function. Now, let's look at some function f of psi prime and multiply it by psi minus psi prime and then do d psi prime. Okay? But you see, f of psi prime is just some very easy thing, right? Because expanded in psi prime, it can only take the form a plus b psi prime, because psi prime square is 0. Okay? Now when we take this derivative, let's take this term, the psi term. Okay. This term will give us, I'll have to take this through and I will get minus b psi. Is this clear? When we do this piece. Because I take the derivative through the psi, that makes it minus, and then I get the psi prime. What about this term? This term on this gives us minus a psi. You see, this with this is 0, because psi prime square is 0. So it's only minus a psi. Minus a, sorry, minus a. Thank you, minus a. So this is equal to minus of a plus b psi. Okay. So now if I did it the other way, okay, so this is very much like a delta function, except I've got a minus sign. So how do I say it in a way that makes it look even more like a delta function? I think I want to interchange the roles of psi and psi prime. So psi prime, right? So exactly. So if I did this psi over psi, then I would get plus a psi prime. Okay. So this quantity plays the role of delta of psi prime minus psi. Okay? It's a quantity such that you integrate over one variable, multiplying by a function of the other, you reproduce a function of the other variable. You have to keep your wits about you for the signs. Okay? So this is the reason we demanded this quantity, because it's the fermionic analog of saying these two states are sort of orthonormal to each other. It's a delta, they click only when psi is equal to psi prime. Okay, great. Now, let me check that I've got the psi minus psi prime right. It's not psi prime minus psi. Let me make sure I've got that. Psi minus psi prime, beautiful. Right. Now there are two more things that we want to check. When psi is psi prime, okay, let's see. So when psi is psi prime, yes, it's true. The inner product would be 0. Okay. You say that's not like a delta function. Yeah. That's your point? Yeah, okay. This is as good as we can get with these fermionic numbers. It has this property of the delta function, that you multiply by a function and you integrate, it has this property. It's true. I mean, you know, psi and psi prime are thought of as being independent anticommuting numbers. So setting them equal, it's not even clear what that means, really. But if in some context, fine. So you're right, it doesn't share that property of that it's infinity. Maybe 0 and infinity are somehow neighbors of each other. Okay. Okay. These are all definitions, you can't argue with that. Okay, great. Now we want to start doing some physics. Okay, so the first thing I want to do is to convince you that integral psi d psi psi is equal to identity. So there's a completeness relation in the space of coherent fermionic coherent states. Are you guys familiar with coherent states for SU2? Have you seen this? It's very similar in some spirit. It's in spirit very similar. It's a fun exercise to go through if you're not familiar with these things. Of course, those are very concrete and non-abstract things. But okay, fine. Okay, so these are sort of fermionic analogs of those coherent states. Okay, so I want to convince you that this is true. How will I convince you of this? Well, I'll convince you of this by acting on this with an arbitrary state and saying I get back the arbitrary state. But the arbitrary state is just some psi prime, just some linear combination of up and down. Okay, so let's check. So what I get is here, suppose I put a psi prime here. So I'm going to take this and act on psi prime. So I get psi, d psi, psi, psi prime. Clear? Now, by our defining property, this was psi, d psi, integral psi, d psi, psi minus psi prime. Okay, now let's open this guy out. Okay, so we open this guy out. This guy was down plus psi times up times d psi psi minus psi prime integration. The d psi being here means that, you know, I should take the d psi out here, but with an additional minus sign. The d psi acts on everything. Not on the first term. Let me check actually. But there's I thought it did. Just a minute. We'll see. We'll see. Let's see. No, I think including on the first term. It's just, let's see. Let this d psi act on everything and see what we get. Okay. First, we can hit this guy on this, which could only have multiplied this. So what this means is equal to minus d psi of every time I take, sorry, what do I mean by this? Just a minute.
You can take the d psi totally out
with 1 minus psi out here. I think that's right. Come. So d psi on down minus psi up into psi minus psi prime. It's giving me psi prime, yes, because of the minus sign. Yeah, thank you. So this guy can, so there are two terms with, I'm just picking out the terms with psi. So that's this with this, okay? There is no, yes, thank you, there's no overall minus sign. Thank you, that would be good. Thank you. So there's this with this, which just gives down. Right, because here I act on the psi. And then there was this with this. Minus and minus cancel to give plus. And then d psi on this gives psi. So plus psi, psi. Right. So this is what this d psi in the middle means here. It just means take the psi through. Okay, and this is the same as psi prime. Okay, so you see that this quantity here is identity. Because acting on any state, it gives back that state. Okay, and note what this means. This derivative is acting on everything. Just the position here means that if it acts on the left, you have to take an extra minus sign. That's what I mean by the position. The derivative is acting on everything, but I've anti-commuted once through with an extra sign. Okay, excellent. So we've got a nice completeness relationship here. We should also check left operation. We can do that. At least using the explicit form of the bra, we can do that. But I don't even think it's needed. If you've got something such that, if you've got an operator, A such that A on psi is equal to psi, isn't left identity or right identity always equal to left identity in a reasonable enough Hilbert space? Can it be that you've got an operator such that its identity acting from the right? Okay, so let's look. So now make a if this was normal kind of Hilbert space, make an orthonormal basis. Take projector from here. It'll automatically be true, right? Which I don't even think it's needed, but you can go ahead and check it. Fine. Okay, good. So now that we've got this guy going, we're going to prove a couple of key identities. Okay. The first one we're going to prove is this. Okay. We're going to prove that integral d chi of minus exponential of chi psi prime minus psi is equal to psi minus psi prime, which we know is this quantity. Okay? So the thing we're going to prove is this algebraic identity. We're going to prove that these two are equal. We already know that this is equal to this. So we will prove that this quantity is this. Okay, we want to get an integral representation for this inner product. This, by the way, is like the integral representation for the delta function. Right, it's e to the power I a x integral over x is delta of a. It's like Fourier, yes. But you see, when we have e to the power I x a integral dx, we get delta of a, right? So this is sort of like this, and this is sort of like that. Yes. Yeah. For fermionic numbers, i's play very little role, since they're all polynomials. So let's see how you prove this. It's very easy. It's very easy because these exponentials are very easy functions. Because you can Taylor expand them, and the Taylor expansion ends at first order. Okay? So this is minus d chi of 1 plus chi times psi prime minus psi. And then it stops, because if you go to the next order, chi square is 0. Okay? So the left hand side is this. Now d chi on 1 is 0. D chi on chi is 1. So this is equal to psi minus psi prime, because of this minus sign, which is what we want to show. Okay, so that's algebraic fact number 1. Algebraic fact number 2 is the following. The next thing we want to show is that psi chi hat psi prime. Okay, so we found and what we've accomplished here is to find an expression for the inner product psi with psi prime in exponential form. Okay, now we will also, when we do the path integral derivation, we will also need matrix elements of chi hat. We don't need matrix elements of psi because psi hat operator acting on psi prime is a number. Right, because the psi hat operator by definition was diagonal. I mean, you remember the psi prime, you remember this equation, right? Psi hat on psi prime was equal to psi prime on psi prime. I don't even know, did we check this? No. Oh, let's check it, sorry. So let's check this. I should have written this at the beginning, I'm sorry. Psi hat on down plus psi prime up. Okay, psi hat was the lowering operator. So psi hat on down is 0. Psi hat on let me write this as psi prime here. Psi hat on, we'll check just a minute. Let's see what happens and then we'll write the right equation. Psi hat on psi prime was this. Okay, so let's write it as it is at the moment. And then we take this operator through and we get psi prime. This is just an operator and it gives you down. Okay? No, it won't matter. Left or right, it won't matter, but let's put it on the left. Okay, this is what I get when I add psi hat on this guy. The psi hat is just an operator. It doesn't have any, it's just a sigma plus on this space. Okay. Now, let's look at this guy. What is psi prime on this? That's down plus psi prime up. This is 0 because psi prime squared is 0. And we get this is equal to psi prime down. So these are the same. No, that operator is just an operator in the Hilbert space. It's just some, it's a matrix. It's a matrix built out of real numbers. Okay? Our rules say that you get minus sign only if one anti-commuting number commutes through another. Now, the operator was the number, operator 0, 1, 0, 0. All the numbers in that operator were, if you make an operator with anti-commuting numbers, that's another matter. But that was just an ordinary operator. Okay, excellent. Fine. So, we don't need the matrix elements of psi hat with psi prime. Because that's obvious, right? If we wanted psi hat psi prime, that would just be psi prime of psi prime. Okay? And psi prime we already have a nice integral representation. That's clear? Okay? But chi is more difficult. This is the analog of when we do path integrals. If you use position eigenstate, if you put completeness in position, momentum is difficult, whereas position is trivial. So in our basis, if you think of it as the analog of the position basis, psi hat is the trivial operator, chi is the difficult operator. It's like the momentum. Okay? So So let us keep going. So we've got, we want to compute this. So claim is that psi chi hat psi prime is equal to minus d chi exponential of chi psi prime minus psi. What? I can't understand. Say it.
The previous statement is psi hat product between psi and psi prime.
This one?
No, the left part.
Yes.
That equation.
Yes. It's not entirely correct because we have to take the psi prime through. You're right. It's more psi prime where this is a number, psi. This is the actual statement. Thank you. And then you anti-commuting it through would do something else. But just inside it becomes psi prime. You have to keep track of the order. Thank you, Sunil. You're right. Okay, excellent. So now I want to prove this statement. Okay, this is easy to prove as well. Okay, because this is psi chi hat, which was raising operator. Okay, so this is same as this. Can you see that? Sorry, can you see this? Because chi hat acting on the path that's up here. Remember, psi prime was equal to down plus psi prime up. Chi hat acting on the up part gives 0. So all that remains is chi hat acting on the down part. But then it's just psi on up. Okay, but what is psi on up? What? What is psi on up? Well, psi on up is the part that was, it's minus 1. Right? How do you see that? Well, we know that psi, in many ways. But one way is that we know that psi on down plus psi prime up, which was psi, is equal to psi minus psi prime. Because psi with psi prime was psi minus psi prime. So the coefficient of psi prime on the right hand side is psi on up. But that's minus 1. Of course, you can see it in many ways. Okay. So this quantity has just minus 1. Okay. But I'm claiming that this quantity has also minus 1. Okay, so let us see that. This is d chi into this exponential is 1 plus something. But the something involves chi. So we throw it away because that would be chi square. So with that insertion of chi, the exponential is just 1. There was this minus sign here, so we get minus 1. So both these two different expressions are complicated looking representations of minus 1. Because you may think we're doing very funny stuff, but it's useful. I'm sorry for the formal nature of this lecture, but you'll soon see it's useful. Okay, great. So now that we've got all this going, we're in business. These are our two key relations. This, I'm just writing down the two key relations once again. Key relation number 1 was that minus d chi of exponential of chi psi prime minus psi is equal to psi prime. Second relation is minus d chi exponential, same exponential of chi psi prime minus psi is equal to psi chi hat psi prime. Now with these two relations we're in a position to move, and of course the third key relation is that integral psi d psi psi is equal to identity. Okay. So now what do we want to do? We wanted a path integral representation. We wanted a path integral representation of e to the power, the evolution operator, e to the power minus I h t. So suppose I want some psi out, psi in. Say this is what I want. I want the matrix elements of the evolution operator on the two-state system. Now what is this H? Well, we don't know what H is. It can be anything because it can't be too complicated. It's a two-state system. Okay, whatever it is, it's function of sigma hat, I call it chi hat, and psi hat. And I will choose always to make to order operators such that psi hat appears to the left of chi hat. You can always do it because we know the anti-commutation relations between the two. Okay, so we can always arrange that. So with this understanding, the most general operator in this two-state system is some function of chi hat and psi hat. Every operator can be built out of that. Okay. Now, and of course identity. Okay, fine. Now what I do is what we always do with path integrals. We break it up into little evolutions. We break it up into little evolutions and we insert identity in the middle. So we got, well, let's start from the left because that's psi in e to the power minus I h delta t. And then we put, we put psi 1, d psi 1, psi 1. And then we put an e to the power minus I h delta t. The times don't need to be the same, but for simplicity we can take it. Psi 2, d psi 2, psi 2, and so on. Okay, let the nth guy be right at the end. We will get psi out e to the power minus I h delta t, and let's say the last insertion was n. Yeah, psi n d psi n psi n. This was psi 2, and there's stuff in the middle here. I'm sorry for the incoherent nature of this equation. Do you know what I mean? Shall I write it again? Okay, and all of these there's an integral side. Okay, now for each of these operators, because this time is very small, we can exponentially expand it and work to first order in the exponential expansion. There's identity and there's H. H was chosen so that all psi hats were to the right of psi. Okay, so everywhere we have a psi hat here, in this psi hat would be replaced by psi in. In this, psi hat would be replaced by psi 1, and so on. Now, there may also have been a chi hat, but chi hat square is 0, remember, as an operator. Okay, so chi hat, if it appears only linearly. Okay, and we know how its matrix element is. every chi hat is replaced by a chi, provided we add this exponential. Okay? So, each of these expressions, so suppose I have psi, so for instance, let's take psi 2 with psi 1. Psi 2 e to the power minus I h delta t, psi 1. This I am claiming is the following. It is integral d chi e to the power minus I h chi and psi 1 chi and psi 1 times e to the power chi, and we have psi 1 minus psi. Is this clear? Because this expression here, we Taylor series expanded, keep only linear term in delta t, so it's 1 plus whatever. The one term, okay, the one term is just psi 2 psi 1, and that will be the one term from here, from this exponential. Okay, and we know that psi 2 psi 1 is this expression here. That's that statement here. Oh, and there's a minus. What? It's there, sorry. Psi 1 minus psi 2, thank you. Okay? And similarly, the other guy is some expression, this h was some expression in chi hat and psi hat. The expression was some polynomial expression because chi hat squared is 0 and psi hat squared is 0. We've arranged it so that all chi hats are on the psi hats are on the right of chi hats. Psi hats acting on this gives psi 1, and chi hats acting on it gives chi from this identity. Then we re-exponentiate. Is this clear? Okay. If you think about it, we do something very similar, or one way of deriving the usual path integral is something very similar. In order to get the eigenvalue of momentum in the expression of q prime p, one easy way is then to insert a complete set of momentum eigenstates. Then the momentum operator turns into p, but then you've introduced a p prime, p times q prime. That's this exponential. This is like p. So it's very similar to that manipulation, the usual manipulation, the Feynman manipulation. Very similar to that manipulation. Just now with anticommuting numbers. Okay. Very good. Go on.
How did my chi and psi 1 pass through this psi 2? Like I need to bring e to the power minus I h chi comma psi 1 del t outside inner product of psi 2 psi 1, right? Because inner product of psi 2 psi 1 gives me e to the power chi psi 1 minus psi 2. So just like in that case.
Wait. Start the question again, please. Sorry.
I Taylor expanded this.
Yes.
And then I got from the psi part, psi hat acting on psi 1, I got psi.
Psi 1.
Chi acting on psi 1 gives me chi.
Yes.
And that needs to move out of this psi 2, right?
Out of psi 2?
Yeah, because then I'll get psi 2 inner product psi 1 as e to the power chi.
No. Which needs to move out? The chi or the psi 1?
The psi 1. Or the chi 2, chi also, because both are anticommuting numbers, right?
Yes. Let's just work this out as carefully as we can. Let's just work this out, and maybe I'll understand your question. This is psi 2. Let's take the example of h equals chi hat psi hat. Let's take that example. Okay, so this would be equal to psi 2 1 minus I chi hat psi 1 delta t psi 1. Okay, this term you agree. Okay, so this term, so this is the sum of two things. The sum of psi 2 psi 1 and then minus I psi 2 chi hat minus I delta t psi 1. Okay, this now we can replace by psi 1. That you agree? Okay, now we use the fact that this guy is minus d chi this. That's okay? So let's write that out. And this guy, so I'm writing out and you tell me if you agree with every step. This is minus d chi exponential of, yeah, the first term is exponential of chi psi 1 minus psi 2, and then the second term is minus I delta t, okay, minus I, I'll put a minus overall outside, minus I delta t integral d chi psi 1 exponential of chi psi 1 minus psi 2.
This is the part I'm having the question.
Okay.
So I'm claiming that psi 1 and psi 2 means so I'm claiming that integral on the right hand side I delta t
Yes.
psi 2 chi cap psi 1 psi 1 this expression.
Yes.
This is equal to chi psi 1 times inner product of psi 2 psi 1, right? So the chi and psi 1 moves out of this expression, right? The commuting numbers and commuting numbers chi and psi 1 moves out of the psi 2 or psi 1 whatever. Chi is an operator. That gives a number, right? Chi acting on.
I see. So wait, you agree that the psi 1 was okay, but you're saying that now when we act with chi hat on this, you're saying we cannot now use that formula. You have to first move psi 1 out. That was your point?
Yeah. So I need to move out psi 1 and I need to move both outside, right? I need to express this as only psi 1, and it's because 2 d chi.
Okay, but you can move it out and then move it back in, right?
I mean, it gives plus sign only if you move out.
If you so say it moves out and changes some signs, then when you move back in, it'll change the same signs. I think it's okay. Try it out with one or two sample things. Yeah. Okay, and therefore it's this exponentiated thing. Okay, great. Great. Try it out, Choparno, and tell me if I said something wrong. Okay. Okay. So now we are finally in business, because now we have a nice path integral representation for each of these matrix elements. And we just have to put them all together. Okay. So what we have now is oh, and by the way, just about your question, this guy, every expression that appears here, and maybe this is important, every expression that appears here is even in anticommuting numbers. That is, the Hamiltonian will always be an even function of the sigma pluses and sigma minuses, because only then will it be Hermitian. So this, if you're worried about moving this through the exponential, that is free, if that was the worry. Maybe I'm not answering your question, but please tell me if I'm doing that. Okay, good. Okay, excellent. So, what?
You just expand the exponential and the exponential is not there. It is like 1.
In this case, it's not even there. It's 1. Yes, exactly. Yeah, right, 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 right. Okay, excellent. So now we just put it all together. So what have we got? We've got each of these, we've got these factors. So we've got now d chi for each matrix element we require a chi. There were n plus 1 matrix elements when there were n insertions of completeness. For instance, when there was 1 insertion of completeness, there were 2 matrix elements. Okay, so the number of chi's is n plus 1. The number of psi's is n. Okay, the d psi's can be and d chi's can be moved through these expressions, through these exponentials, or through the Hamiltonians, because those are all even in anticommuting numbers. Okay, so we get a final expression of this form. The first integral, let's say the first integral had a chi, that was d chi 0, let's call it. And then there's a d psi 1, d chi 1, d psi 2, and it keeps going until you get a d chi n. This is d psi n. This was the integral structure. Okay. Every time we use one of these expressions, there was a factor of minus 1. So there was a minus 1 to the power n plus 1, because there were n matrix elements. Okay, and then we get this integrand, which is now very easy. It's exponential of minus I h. So the first guy was chi 0 psi in, right? The first guy was chi 0 psi in delta t plus h chi 1 psi 1 delta t. Okay. And the last guy is plus h chi n psi n delta t. So much for the Hamiltonians. Okay, and in the exponential we also have, there's also exponential of chi 0 into psi in minus psi 1 plus chi 1 into psi 1 minus psi 2, and then the last will be plus chi n into psi n minus psi out. That's out. All good? Now, the numerator here is what? It's a discretization of exponential of minus I h chi psi dt. Okay, plus x chi psi dot dt. Okay, so now we've got a sort of Lagrangian. Sorry, I should put that. We've got a sort of Lagrangian because we've got exponential of I into minus h, and now we didn't have an I here, so we'll make it minus I. Okay, so we declare that our Lagrangian L is equal to minus I chi psi dot minus h. And with this Lagrangian, we have a path integral representation. There's one more thing though. There's one more thing, which is this irritating sign. There's minus 1 to the power n plus 1. So you know what we did was define our measure like this, d chi n, d psi n, so on. Suppose we flip the whole thing around so that the measure is defined as d chi 0, d psi 1, d chi 1, d psi 2, up to d chi n. Suppose we flipped those around. What price would we pay in sine? Exactly. But the price we would pay would be, well, we'd get the first flipping, taking psi 0 all the way through, would give us 2n sines. The total number of variables is 2n plus 1. Because there are n plus 1 chi's and n psi's. The second flipping would give us 2n minus 1, and so on. Now, so we would get, the sign we would get would be minus 1 to the power sum over all the numbers from 1 to 2n. Right? Now, sum over the numbers from 1 to 2n is n into 2n plus 1. Now, no, look. Suppose n is odd. Then this number is odd because 2n plus 1 is always odd. But suppose n is even, then obviously this number is even. So this is the same as minus 1 to the power n. Okay, so after flipping all of these guys, we get this minus 1 to the power n. That almost eats up that minus 1 to the power n plus 1, leaving 1 minus sign. Okay, so the final our final answer is minus psi out e to the power minus I h t psi in is equal to d chi 0, d psi 1, d chi 1, d psi 2, d chi n of that expression, of this guy. This we will sometimes call d chi d psi. It's the fermionic path integral measure. Maybe I should call it some fancy thing. D chi d psi. Okay? So we found how to make path integral representations of Hamiltonian evolution in a two-state system. Okay. Now we've not gone as far as I hoped in this lecture. It all took long. Do you guys think I'm doing too much detail? I could at some point say, you do the algebra and you find this. The danger with that is I might say the wrong thing. Because when you work it out, you're sure you're right.
So if this is a long enough course, I guess it's okay.
It's okay. We can go on forever. We'll go on asymptotic infinity. Okay. So, okay. Okay. Yeah. Yeah. I suspect that if I start cheating on algebra, I will cheat myself. I will forget what is right, and it's not a good idea. I mean, that requires a level of preparation that Onkar is capable of. But okay. but okay. Okay, fine. Okay, great. I think we will have to stop soon, but I'll just tell you what the main point, the point I wanted to make was. Now that we have this expression, the Lagrangian for our Hamiltonian system. The Lagrangian for our Hamiltonian system is now very clear. Okay? Because the two-state part we dealt with this, and the remaining functional part we do the usual tricks. Okay? So let's write it out. We wanted the Hamiltonian that we were interested in. Okay? The Hamiltonian we were interested in. So we imagine doing this in two steps. First, we imagine doing the 2 cross 2 part of the Hamiltonian. Turn that into a path integral. And then we do the position part of the path integral. Okay? So now the 2 cross 2 part of the Hamiltonian had this sigma 3. Sigma 3, you can easily check, is equal to psi hat, chi hat, or is it chi hat psi hat? Chi hat psi hat 2 chi hat psi hat minus 1. Why? Chi hat was the raising operator, so it's 0, 1, 0, 0. Psi hat was the lowering operator, so 0, 0, 1, 0. So if I do 2 of this, what do I get? I get 2, 0, 0, 0. Right? Because this into this is. Okay? And then if I do minus 1, that becomes 1, 0, 0, minus 1. Okay? So where we had sigma 3, we should replace this by 2 chi hat psi hat. And then I've intentionally done it so that psi hat was on the right. And so we conclude that our path integral is the matrix element minus the matrix element is equal to d chi, d psi, this thing, exponential of, and then of course now we also put in the dx, right? Or d little x. And then we get x dot square by 2 minus w squared x by 2 and then we will get minus, because it was in the Hamiltonian. So we had this thing which was, what was it? I h cross sigma 3 w prime, right? No I, just h cross. Okay, this. Now that becomes, okay, first we put in our kinetic term, which was minus I chi psi dot. Let me write. First kinetic term. Okay. So we get exponential of, let me set h cross equals 1. Okay. There was an I here, and in the kinetic term, there is a minus I. So minus chi psi dot I'm setting h bar equals 1, you can restore it later. Okay. Minus I psi dot, and then there's minus h. There was a minus w x square by 2, ordinary negative of the Hamiltonian, the term that had no, and then we want minus this Hamiltonian. So that's minus of chi psi, minus 2 chi psi minus 1 w prime. Ah, good point, good point, good point. The chi-psi should have an I. So, because L itself has an I. So, we got we exponentiated that with an I. We exponentiated that with an I. Yeah, just give me a minute. Right. Our Hamiltonian had an IH, right? IH, so there was an I outside there. Did I miss that I somewhere? Yeah, I is outside there. Yeah. So that I is there, that just, I think it's okay, right? You're probably right, sorry. You're probably right. So we want to write this whole path integral as, no. Sorry, you're right. I got this I wrong. This guy, if I write an I, has a minus I. So, yeah, thank you. So this was okay. It's that I got this wrong. This was minus I. Okay. Now, my task next time will be to show you, the first thing we will try to do next time would be to try to show you that this path integral itself can be seen through path integral methods to be supersymmetric. Okay, and in doing that we will introduce superfields to make these manipulations easier. Okay, let's stop here.
This is why you were saying that this should be quadratic in the variables. There is no linear in psi or chi.
Yes, there never will be. There never will be. You see, because the Hamiltonian itself, if it were, odd in psi or chi, would not be able to be Hermitian. Okay, so Hamiltonian has to be, and the kinetic term is what it is. Yeah. So what appears in the integrand in the path integral is always in the end Grassmann even though individual terms may be Grassmann odd. Okay. So let us continue this next time. We will try to revert this now. We will try to see that from this Lagrangian formalism, the supersymmetry is manifest. Okay, and once we understand that, in subsequent lectures, we will continue for maybe two more lectures on supersymmetric quantum mechanics. Where we're going is to try to understand the supersymmetric quantum mechanics of a particle not moving in one dimension but in many dimensions. Okay, in that problem, something nice happens. As we will discuss. I may have to take a lecture on some mathematics before we go on to that problem. But okay.